So first, a reminder that we're going to have our second midterm this Thursday. It covers everything from hash table to what we discussed last Thursday, which is the shortest path in weighted graph. Okay, so today we're going to talk about something called spanning tree. So far we look at graphs, be it direct or undirected. We talk about how to traverse the graph and how to compute the shortest path in weighted graph. Okay, so today we're going to look at a different graph problem, which is to compute the so-called minimal spanning tree of an undirected graph. Now here we're going to talk about undirected graph because if the graph has direction, the edges has direction, then the spanning tree is not really well defined. Okay, all right. So in today's class and also in fact the next class, we're going to focus on undirected graphs. Okay, all right. So let's first look at what is the spanning tree. Well, so first, we've mentioned that trees before. So what is a tree? Formally, an undirected graph is a tree if and only if the following two conditions hold. Okay, number one, it has to be connected. Okay, number two, it cannot contain any cycle. Okay, so it turned out that, so for example, the following is a tree. Okay, now it turned out that if a graph is a tree, then the number of edges must equal to the number of vertices minus 1. Okay, so intuitively, why is this the case? Well, intuitively, let's say that you have V nodes. Okay, now let's imagine that we grow the tree one edge at a time until we got we add edges one by one. Okay, so now at the beginning, all these nodes are not connected. But remember, if T is a tree, then it has to be connected. So we're going to add edges in T one by one, and every time when we add a new edge, then we basically connect to yet another component. So we reduce the number of connect components by 1. Okay, so now in order for me to reach all other nodes, it doesn't matter how the tree look like, but in order for me to reach all other nodes, I have to add V minus 1 number of edges in order to reach them. Okay, because at the beginning, all these nodes are not connected. Okay, so that's why that intuitively the number of edges equal to V minus 1. It cannot be more than that because V minus 1 number of edges is sufficient for me to connect them. If you add any new edge, okay, let's say this one, okay, if it didn't reach a new component, what does it mean? That means the two endpoints, U and V, are already connected, like in this blue path. Okay, then when you add a new red edge to connecting them, then you have two ways to connect them. You form a cycle. So, okay, so it cannot be. So every edge you add, you have to reach a new component, connect to a new component, merge a component, and you can only do so exactly V minus 1 number of times. Okay, to kill all the connect components. Okay, so you go connect components, start with V connect components, that's a V number of nodes. In the end, you have only 1 connect component. Okay, every edge will kill 1 connect component. Okay, so that's why the number of edges equal to, in a tree, equals to exactly V minus 1. Okay, so this actually gives us an alternative definition for a tree. So this is equivalent definition. An undirected graph is a tree even only if it is connected. Note that the tree has to be connected and the number of edges equal to V minus 1. Okay, just some examples. This is a tree. We have, everything, all the nodes are connected to each other and there's no cycle. This is also a tree. Okay, it's a different tree on the same set of nodes, but it's also a tree. And this one, is this a tree? Well, we have here we have a cycle. So this is not a tree. Okay, even though it's connected. Okay, you can also verify this one. The number of edges is more than V minus 1. Okay, so it's not a tree. This one, do I have cycle? We don't have cycle. Okay, however, this one, this is not connected. Okay, nodes here cannot reach nodes here. Okay, so you can also verify in this case the number of edges is smaller than V minus 1. Okay, all right. So there are different definitions of trees. You can use whichever that's convenient for you. Okay, sometimes it's easier to use this definition I'm showing on this slide because then you just need to check the connectivity and also check the number of edges, relation between the edges, number of edges and the number of vertices. Okay. All right. So here are some important properties of the trees that some of those that we're going to use later in our algorithm. Okay. So suppose T were given the tree. Okay. Then given any two nodes in the tree, let's just pick any two. Okay. Say this one and this one. Okay. Pick any two nodes. There is a unique path between them, okay? Because this is a tree, then I can just follow the tree. That has to be connected, so there must be a path connecting them. And you cannot have more than one path. Why? If between two nodes you have more than one path, then it closes up into a loop, a cycle, okay? So you cannot. So between any two nodes, so between any two nodes, we have exactly a unique path connecting them. Okay, you can verify this for any two along the tree. Okay, so that's condition. That's a property number one. Okay, the second one is that, so suppose we already have this tree. Now if you want to add another edge, okay, so everything's already connected. Now every time you add another edge to this tree, it doesn't matter which two. Let's say that now I want to add this edge E. Then this edge E must create a unique cycle which consists of the unique path in the tree connecting the nodes U and V plus this edge E itself. Okay, so this gives you see, I would have a way to connecting them. Adding this edge close that loop. So I got a cycle. Okay, so the adding any edge to E to the tree will create a unique cycle containing E. Okay, so that's this actually the cycle equals to E plus the unique path. So let's say E equal to UV, unique path from U to V in the tree. So this gives you the cycle. Okay, all right. Okay. So here's another example. So if here I added this edge E, then the unique path between this endpoint are the green path, and the cycle is the green path plus this red edge. Okay, all right. Now, another property is that this tree right now, so we're given this tree, it is connected, okay? If I remove any edge, okay, let's say that I remove this one, then that must disconnect the tree, okay? This is because that if you remove an edge that considers this two endpoint, this used to be the only way to connect them. Remember, there's only unique paths connecting them. By removing this edge, these two nodes are not connected anymore. Okay, so it's rather intuitive. Okay, so intuitively, all of this suggests what is a tree. So if you have n nodes, okay, if you imagine all possible graphs connecting all these n nodes, okay, a tree basically has the least number of edges, which is exactly n minus 1. Okay, so here n is your size of V. Okay, so in other words, if I have n nodes that I want to connect, okay, and the most economical way in terms of the number of edges is using a tree, which would use V minus 1 number of edges to connecting them, and that as a consequence, there basically you don't have any redundant edge. There's no cycle. Okay, all right. So that's what a tree is. Okay, so now suppose we're given a graph. Okay, this graph may not be a tree. Okay, now given this graph, a spanning tree of this graph is basically any subset of edges in your graph, okay, who actually connects all the vertices and also doesn't have cycles. So namely, it's a tree that touches all the vertices in your graph. Okay, so let's see. Suppose this is my graph. This one is not a tree. Okay, so what is a spanning tree? So if I pick some subset, let's say I pick this one, this one, this one, this one here. So note that the red edges is a subset of edges such that I connect all the nodes. Okay, so the set of nodes together with this red edges is a tree. Okay, it connects all the nodes and there's no cycle. So this one is called a spanning tree of this graph G. Okay, and obviously the spanning tree is not unique, right? So this red one is one example, or I can give you a different example. I'm going to clear this, and then now let's look at using orange one. I can do this. This is another tree. Okay, so it's a spans. It's called a spanning tree because it touches all the vertices, and it must be a tree. There's no cycle. Okay, so just remember that this is what it means. It touches, it spans, namely it touches all the vertices, connects all the vertices, and yet it doesn't have any cycle. Okay, it's a subset of the original graph. Okay, so this is another spanning tree. Okay, how about this one? How about this one? Is this a spanning tree? Well, there's no cycle. However, note that this one is not connected, right? So it's not this orange edges doesn't form a tree. So this is not a spanning tree. Okay, so this is not a spanning tree. I can, if I add this edge, now this becomes a spanning tree. Okay, but if I also add this edge, then it's not a spanning tree again, because now I have a cycle inside. Okay, this edge is redundant basically. Okay, all right. So one way to think of a spanning tree is that you give me this graph, it shows, and then I'm now going to use a subset of the edges, a minimal set of edges to still connect all the graph nodes. Okay, so that's intuitive of a spanning tree. Okay, so here's another spanning tree example. All right, as I just said, intuitively a spanning tree of G contains the smallest possible number of edges in G, in E, in your input graph in order to connect all nodes in G, okay? Okay, now, obviously, if your input graph is not connected, then you cannot find a subset of edges that connect all the nodes, right? So there doesn't exist any spanning tree in that case, okay? But in the literature, sometimes you can still talk about the spanning forest, which consists of a set of spanning trees, one for each connect components in G. Okay, so for example, in my G looks like this. Okay, so if this is my input G. Okay, so now these are not connected, so I cannot find a spanning tree of this. However, I can find a spanning forest. So the blue one will be a spanning forest, which is the spanning tree for each connect component. Okay. At any rate, let's assume in the remainder of this class that the graph we have is connected, and then we're going to compute the spanning tree. Okay. All right. Okay. So now remember that our graph can also have edge weights. Okay, so the same holds for the spanning tree now you're taking. Okay, so the weight of a spanning tree of a weighted graph is simply the total weights of all edges in the spanning tree. Okay, so the weight of a spanning tree simply equals to the sum of, for all edges in the spanning tree, the sum of their edge weights. Okay, all right, and so for example, here I'm showing a graph, and the shaded edges form a spanning tree of this graph, okay? And then what's the weight of this tree is simply the total sum of all of this. So the weight of this tree equal to the sum of edge weights in the tree, which is 10 plus 8 plus 8, 10 plus 8 plus 8 plus 5 plus 2 plus 6 plus 3 plus 1. Okay, and then you can calculate it. I think the total equal to 43. Okay, so that's the weight of the spanning tree. Okay. Okay, so now, as we said earlier, given the same graph, I can find different spanning trees, different ways to connect all the nodes. Okay, and this different spanning tree has different weights. Okay, and what we're looking for is the one with the minimal weight, and that is called a minimal spanning tree, which I often denote by MST, minimal spanning tree. Okay, so a minimal spanning tree of a weighted graph is basically a spanning tree whose weight is smallest possible. Okay, and it turned out that I think in this example, this tree also is the spanning tree with the minimal possible weight. Okay, so for example, if you remove this edge from the spanning tree and then add this one instead to connect all the nodes, then the weight would be higher. The weight would be 45 instead of 43. Okay, all right. Okay, as I mentioned already, spanning trees given a graph may not be unique. Okay, there are many trees spanning all the vertices. Okay, and the minimal spanning tree also may not be unique. Okay, there are multiple trees. There could be multiple spanning trees, all have the smallest possible weights. Okay, their weights are the same, but the tree may not be. Okay, so for example, here, can you see how to modify to get another? I already told you this shaded tree right now is a minimal spanning tree. Okay, then note that I could remove this edge and add this edge instead. Now the total weight does not change. Okay, because I replaced the one. You can verify this is still a spanning tree and the weight doesn't change. Okay, all right. So, but we do know that all the minimal spanning tree, they have to be spanning trees to start with. That means that they all have the same number of edges. They all have v minus 1 number of edges. Okay, because any spanning tree of a graph of v nodes has v minus 1 number of edges. Okay, all right. So here's a question. Let's assume that all edges in the input graph has the same edge weights. Okay, in this case, how can I find the spanning tree of it? Okay. And the question is that if all the edges have the same weight, okay, what do you think is the weight of a minimal spanning tree? Well, note that any spanning tree has to have v minus 1 number of edges. And if all the edges has the same weight, let's say 1, then that means that all the spanning tree has weight v minus 1. Okay, that means that any spanning tree would be a minimal spanning tree if your graph has equal edge weights. Okay, so then all we need to do is just to compute any spanning tree of the graph. Okay, and the question is, how do you do that? And in fact, remember that when we perform BFS or DFS, we actually got a BFS tree or DFS tree, and that is a tree that spans all the nodes. Okay, so we can just use, in that case, either BFS or DFS to find a spanning tree of the input graph, which is also has to be a minimal spanning tree because all of them has the same weights. Okay, so you can try to design an algorithm offline to do what I just said. Okay, so we know how to find the minimal spanning tree if all edges has equal weights, say weight 1. Okay,